Hello, welcome back to another episode of Math with Haas. This is Precalculus Season 1, Episode 11. We are continuing our investigation of exponentials and logarithms. So, at this point, we've covered the core of what are exponentials and logarithms, their properties, their laws, their graphs, how to solve equations. Now it is time to look at some applications of these functions in the real world. So what we want to do is consider, suppose we have a bacteria, just a single little bacteria here, and suppose our bacteria takes it 1 hour to undergo mitosis, and so then we get 2, so 1 hour later. I should move this down here. Let's do that. So this would be 0 hours because we're starting out. 1 hour later, we have 2 because we're saying suppose we have our one bacteria and it takes an hour for it to undergo mitosis. Now, since it takes an hour to undergo mitosis, 2 hours later, we will have 4 because each of these will split into 2, and that gives us 4 little bacteria. And we think 3 hours later, that will give us 8 bacteria, 4 hours, 16, and so on. And we can extrapolate our pattern here. So we have 1, 2, 4, 8, 16. So then if we think about this as a function of time, we can notice that 2 to the first will give us 2. But if we take 2 and we square it, that'll give us a 4. If we take 2 and we cube it, that's going to give us an 8. Take 2 to the 4th, that'll give us 16. And if we remember that 2 to the 0 is 1, then the population of our bacteria follows this basic form here. So the population would equal 2 to the t. Now, if we start with like 20 bacteria now, so if we have 20 of these bacteria, and then they start doubling, well then we would have 40 as our first. And then how many would we have after that? Or would we have 40? That's a question. So what we want to think about it is this way. If it takes the same population 1 hour, if it takes a single bacteria 1 hour to undergo mitosis, and now we have 20 of them, what we want to do is think of it as 20 times 2 to the t. So if this is t equals 0, we have 20. If t is equal to 1, then you have 2 times 20, which is to 40. If we have t is equal to 2, then we have 2, or 20 times 2 squared, so 20 times 4, which is 80. Right, we can just keep multiplying this by 2, I think 160, and so on and so forth. So this is where this pattern is coming from. We can see that if we have some initial population, which is what this 20 represents, then we can see that we can interpret it as our 2 to the t, but multiply by 20 here. So we're going to revise our formula. So our population will equal, let's say, p naught 2 to the t, where p naught is our initial population. That is our starting population. Or you think your beginning population. Now, suppose there's another bacteria, and for this second species, it takes instead 4 hours to undergo mitosis. So in our first bacteria, it required only 1 hour, but now we have 4 hours. It takes 4 hours instead. So if we have a single bacteria, then this is at 0 hours. Now we have 4 hours, and we have 2 bacteria, 8 hours. We have 4, 12 hours. We have 16. So in order to fit it in this model here with a 2 to the t, what we need to do is think about how can we change our time inputs, because we clearly don't want to be plugging in 2 to the 4th in order to account for our 2 bacteria here, because 2 to the 4th is actually 16. So we need some way of reducing this time value. And what we're going to do is divide it by a value. So we said that it takes 4 hours to undergo mitosis. So if we modify our equation to be 2 divided by this value, I'm going to call this value d. So in this case, d is going to be 4. So we have 2 to the 4 over, or t over 4. Then when I plug in my 4, that's going to be 4 divided by 4. So that's 2 to the first, which will give me the 2 here. I plug in my 8. That's going to be the same thing as 2 squared, which is 4. If I plug in 12, well, 12 divided by 4 is 3. Oh, I just realized this should have been an 8. Oops. Mistakes happen. So if I take 12 and divide by 4, that gives me 3. 2 cubed is 8. So what this d represents is the doubling time, the time it takes for a population to double. So let's summarize. So our population, we could think of it as p naught times 2 to the t over d, where p naught we said was initial population. But now we have this quantity d here, and that's going to equal the time it takes for the population to double. Oops. Time required for population to double. The short way of saying this is just doubling time. Alright, so this equation here models what's called exponential growth, and this is the doubling time model. Exponential. Alright, butchering the spelling here. Exponential growth, there we go. And this is, again, the doubling time model. Alright. We could have just as easily derived an equation for that. Instead of doing tripling time, we used, or I mean, instead of doubling time, we did like tripling time or quadruple time. But usually we're more interested in figuring out how long it takes for a population to double. Now, let's go ahead and work through a nice example with this. So, let's go ahead and type out a example. This suppose you have a bacteria population of 1200 that doubles every 5 hours. Alright, so we're given an initial condition, we are given a doubling time. So now here's some questions. 1, find a model for this population. 2. How many bacteria are in the population after, how about 20 hours? And 3. How many hours will it take for the population to reach 1 million? Alright. So, to answer question 1, what we want to do is note that this right here is our initial population, so that's P naught. We'll go ahead and box that. And then we are told that the doubling time is this right here, every 5 hours. So this is our D value. So then to answer question 1, we can say that our population is going to equal 1200 times 2 to the T over 5 power. And that is our model. It's as simple as just that. The main thing is just recognizing what variables correspond to what quantities given in the question. Now to answer question 2, we're given this 20 hours here. So this is a value for time. And when it asks how many bacteria are in the population, this is a question asking what does P equal? Okay. So when it asks how many population are in the population, did I just say how many population are in the population? Should be how many bacteria are in the population. So when it's asking how many bacteria are in the population, we are looking for what is P equal to. So in this case, we have P, it has to equal 1200 times 2. Now, since we are given a T value, we plug into 20 over 5. And so now we can just plug this directly into our calculator. 1200 times 2 to the, well, if you didn't know that 20 divided by 5 was 4, you can just be lazy and plug it in as that. And we get an answer of 19,200 bacteria. Alright. So that's pretty good for 20 hours. But now this raises the question, how long will it take for the population to reach 1 million? So let's go ahead and highlight this. So this question here, how many hours will it take? That, let's use a different color here. So this is a question asking what does T equal? Okay, so we're looking for a time value, and what we are given right here is P. So we're told that P is equal to 1 million. Alright, so we're looking for T, and we are given 1 million. So we can set up our equation now. So we have 1 million is equal to 1200 times 2 to the T over 5. Now this is just a nice exponential equation, and if we recall from our previous videos, our first step is to isolate the exponential. So our exponential is this term right here that I highlighted. We need to isolate that. So we'll divide the 1200 out. So divide by 1200, divide by 1200. Let's see here. 1 million divided by 1200. Let's see what that gives us. Alright. Let's turn this into a fraction. Alright, 2500 over 3. So 2500 thirds is equal to 2 to the T over 5. Now the second step of our process for solving exponentials is we go logging. We must take the logarithm of both sides in order to bring that exponent here down using the law of logs. So I'm going to use the common logarithm. So we have log of 2500 thirds is equal to log of 2 to the t fifths. And then we need to recall our law of logs now. So log of a to the c is equal to c times log of a. And that's what we'll use for the right side. So we get log of 2500 thirds equal to t fifths log of 2. Now, this quantity here is simply just a number. It's just simply a number, just log of 2 divided by 5. That's all just a number times a variable. So I'm going to divide out both sides, or we can think of it as multiplying. So I'm going to multiply both sides by 5 over log 2. So times 5 over log 2. And that will give me t is equal to log of 2500 thirds, well, 5 times that over log of 2. And let's see what this value is. So 5 log of 2500 thirds divided by log of 2. And we get 48.5 hours. Okay, so t will equal 48.5 hours. So it just takes just over 2 days and you get the population will reach 1 million. That's not very long. Alright. So this is an example of working through a problem of exponential growth involving doubling time. However, suppose we don't want to think of a bacteria population in terms of doubling time. Suppose we want to think of it as a continuous change, or in other words, a relative growth rate. So if we recall from before, when we discovered Euler's number, that is E here, the claim was that we could use this to model continuous changes. What's the population happening for as it changes continuously for every moment? And when we create a model using E, that will give us a relative growth rate model. And that's what we're going to figure out now. So to determine the relative growth rate, let's see. So to determine relative growth rate, what we will want to do we'll state the equation. So our population is going to equal, it'll look very similar. In fact, we've already seen this before. P naught times e to the RT. So P naught is the same, E is the same, P and T are the same. So this R is going to be our relative growth rate. So the question is going to be, what is the relationship between relative growth rate and doubling time, those two different models? So what we can do is we'll think about it this way. So if this is the relative growth rate model, we want to think about how long does it take for a population to double. So if you have a initial population of P naught, the question is how long will that double. So we're interested in when does P equal 2 times the initial population here. So this is how we'll set it up. So we can see in order we can see that with our setup here, we can divide out the P naught from both sides. And that just leaves us with 2 is equal to e to the RT. This is an exponential equation. We could just take the natural log of both sides, since natural log is log base e. So natural log of 2 will equal natural log of e to the RT. And the natural log and the e, they will cancel each other out using this property of logs. That natural log of e to the x, same thing as x. So we have natural log of 2 is equal to RT. So if we divide by t here, this tells us that r will equal the natural log of 2 over t. So this gives us a relationship between rate and doubling time. So I guess now that I think of it, if we want to think of it in terms of t, we could just divide out the r instead. So you can have time is equal natural log of 2 over r. Alright. So this is actually how we can convert between doubling time and the relative growth rate model. So we should probably work through an example of that. So if we have, say, 1,000 bacteria, that doubles every about 40 minutes. Alright. Now, before I dive into this, since we were looking for doubling time, this t value, that's actually going to be d. I just thought I should make it more clear. So our doubling time is going to equal it's equal to natural log of 2 over r. So this is how we will convert from relative growth rate to the doubling time model. Alright, so if we have this, we know we could write this in terms of the doubling time model as 1,000 times 2 to the t over 40. So I'm going to assume time here is in minutes instead of hours. So the previous examples, time was assumed to be in hours. Now I'm just going to work in minutes to make this easier on us. So this is our equation, and if we want to figure out how to turn this into a relative growth rate model, we can note that d is equal to natural log of 2 over r. So our d here was 40 minutes, so this is equal to natural log of 2 over r. Or we could think of our other quality over here. R is equal to natural log of 2 over t. R is equal to natural log of 2 over t. Let's see here. So if we have that, then we can just plug in our 40. So the rate is going to equal natural log of 2 over 40. Let's plug that into the calculator. Natural log of 2 divided by 40. And that right there is going to be our growth rate, about 1.7%. So we can write this in terms of relative growth as p will equal 1,000 e. I like just to use natural log of 2 over 40 times t, simply because if I use natural log of 2 over 40 for my calculations, I will get the exact value. Or versus if I use a 0.0173, and if I round, so I rounded and cut off all these other digits, then my answer will be off slightly. And we'll do an example showing that. So if I want to know the population, say 50 hours later, and if I used our correct value of natural log of 2 over 40, so e natural log of 2 over 40 times t, versus if I use this equation here where I rounded, let's see what the difference would be. So this would be 0.017 t. So we have to plug in 50 in both cases. So we have 1000 e to the, well, since I have this value saved in my calculator already because it's the previous thing I did, I'm going to hit second and this button here because A and S is that memory slot with the previous value. I'm going to multiply that by 50. So 50 hours later, I should get 2378. I'm going to round down because we have a 0.14. So you want to think, if you're answering a question, you would give this as your answer. But since we are going to compare the numerical values, I'm going to go out a couple decimal places here. So if we do the other one, we have 10,000 e to the 0.017 times 50. Let's see how many bacteria we're at. We are missing about 40 bacteria. So this is 2339.6468. So this would tell us that we have about 2,339 bacteria. I'm rounding down for both values, whereas here we have 22,378. That's a difference of 39 bacteria. So that's quite a bit of bacteria. It'd be even more problematic if it was something like tigers or lions. When you do, or those, if you have like an endangered species, those 39 extra animals you're missing would be a huge error. And you're probably wondering, well, what if we did, we can try this again with a 73T, just use another extra digit, see how accurate that would give us. So let's go ahead and edit this. Insert 3. Alright, so that is a relatively accurate one. So this would give us 2375. So notice if by going out to 4 digits of accuracy, we're missing 3 animals, versus if we went 3 digits of accuracy, you're missing 39. Now I'm curious to see how many animals would we miss if we only went to 2 decimals. So this is a 0.017, so I'm going to round this to 0.02. This would be very bad to do. Let's see here. That gave us more animals than we had. 40 animals more. Okay, so you can see how rounding gives you all sorts of values depending on how you round it. This is why I like to use the natural log 2 over 40. Now if I had given a problem that required using this value over and over, what you would want to do is natural log of 2 divided by 40, and you want to store that. So I'm going to hit STO for store. I'm going to put that in memory slot A. Now notice, if I just put an A in, there's my number, and it will stay there. So if you want to do math with that number, you can figure out like what is A squared plus A. So this is 0.017 squared plus itself. Didn't change that much. If you want to know what 50 times that number is, you can just do that, and there you are. So it's very useful to be able to use the memory slots there. I highly recommend it. Well, we have gone long over what our usual video lengths are, so let's go ahead and summarize really quick what we did here today. So we have a model of, we looked at exponential growth, and we had 2 models. We had the doubling time, So that was P is equal to P naught 2 to the T over D. And we had relative growth rate. So relative growth rate. And so this is P is equal to P naught E to the RT. So in both cases, P naught is equal to the initial population. D is equal to doubling time. And in this case over here, R is going to equal relative growth rate. Alright, if you've enjoyed this video, please consider subscribing to our channel and support us on Patreon. I thank you very much for your audience, your viewership. It is satisfying to know that these videos are helping you. So please stick around. We have a lot more work to do when it comes to modeling. There are more models ahead of us. So thank you for joining our math party, and we will see you next time.